Welcome back to AI Paper Podcasts. Today we're diving straight into Context Engineering 2.0, the context of context engineering. This is a really important piece by Kishuofua and colleagues from SJTU, SII, and GAIR.
It really is. It lays out, well, basically a blueprint for how we should think about context in AI systems.
Exactly. Not just managing it, but understanding its history, the theory behind it, and the architecture needed going forward.
Right. And if you just need the quick version, say for a short edit, here are the 4 absolute key takeaways for a technical audience. First off, context engineering, CE, it's not some brand new thing. It's actually been around for over 20 years, evolving out of early HCI and ubiquitous computing.
Okay, point 1, not new.
Point 2, at its heart, CE is about entropy reduction. Think of it as the work needed to bridge the gap between messy, high-entropy human intentions and the clean, low-entropy structured input machines need.
Makes sense. Bridging the gap.
Third, the paper maps out 4 evolutionary stages. Era 1.0 was the passive executor, and we're heading towards a speculative era 4.0, the considerate master. This whole evolution is driven by machines getting smarter and tolerating more messy context. We're currently moving from 2.0, the agent-centric stage, towards 3.0, human level.
4 stages, moving from 2.0 to 3.0 now. Got it.
And finally, the big future challenge, building what they call a semantic operating system. This system needs to manage, abstract, and apply context across a user's entire lifespan. That's the key to real human-machine symbiosis.
A semantic OS. Okay, that's a fantastic roadmap. Let's unpack that core idea you mentioned first, entropy. The paper really hammers this point. Humans are good at dealing with messy information, filling in blanks.
Yeah, we have common sense, world knowledge. We reduce information entropy almost subconsciously. Machines, not so much.
Right, so if I send you a rambling voice message, you can pull out the key points. A machine struggles with that raw, high-entropy input.
Exactly. And that effort, that whole systematic process of designing how we collect, store, manage, and use context, that's context engineering. The paper defines it almost like a function. CE maps context C and a task T to a usable form F context. It's the cost of translation.
Ah, okay, so the cost goes down as the machine gets smarter, because it can handle more of the mess itself.
Precisely. The history of CE is basically the story of machines shouldering more of that entropy reduction burden.
Which we can see playing out across those 4 eras they defined. Let's walk through them. Era 1.0, say the 90s up to around 2020. Primitive computation, the passive executor.
Yeah, back then, context was essentially pure translation. You needed really rigid, structured stuff, drop-down menus, specific command line arguments, maybe sensor data like GPS.
So the human was doing all the work of translating their intention into that rigid format.
Absolutely. Humans were the intention translators. Think of things like the early context toolkit or projects like Cooltown mapping digital info onto physical places. The systems had, well, almost zero tolerance for ambiguity.
Then came Era 2.0, kicking off around 2020 with models like GPT-3. This is the agent-centric intelligence phase, the initiative agent.
Right. And here, context shifts from being translation to being instruction. Machines suddenly got way better at understanding natural language, handling much more raw, high-entropy text.
So this is where prompting, RAG, retrieval augmented generation, and tool calling come in.
Exactly. Those are the core mechanisms of Era 2.0, and that's pretty much where we are right now. The machine is a powerful assistant, but it's still mostly reacting to our instructions, even if those instructions can be much fuzzier.
Okay, so looking forward, Era 3.0, human-level intelligence, the reliable collaborator. What does context look like then, if we get there?
Context evolves again, this time into the scenario. The idea is that agents won't just understand text, they'll assimilate much richer, higher entropy social cues. Things like vocal tone, maybe body language from video, emotional states, subtle interaction patterns.
So understanding the whole situation, not just the words.
Exactly. That assimilation of social context is what enables truly natural collaboration, moving way beyond just processing text commands.
And then the really out there one, Era 4.0, speculative, superhuman intelligence, the considerate master.
Yeah, this is where context becomes the world. The paper suggests the relationship kind of flips. Machines don't just understand the context you provide, they proactively construct context. They anticipate needs you might not even realize you have. They could even potentially guide human thinking.
Like the Go AI example they mentioned, where it came up with strategies humans hadn't conceived of.
Precisely. Its understanding of the world, the game of Go, was so deep it could guide professional players. That's the kind of paradigm shift Era 4.0 hints at.
Okay, that considerate master idea guiding human thought. That definitely raises some interesting ethical questions, doesn't it? Feels a bit like machine paternalism.
Oh, absolutely. That's a huge boundary we'll need to navigate very carefully. The paper mostly frames it technically, what could a machine do if it understood the world that well, but yeah, the societal implications are massive.
But putting those Era 4.0 questions aside for a moment, the engineering challenges start much earlier, right? Back in Era 2.0 and 3.0. If machines struggle with entropy, how do we even design the systems to collect and manage context effectively now?
Exactly. Which brings us to the design considerations. First step, collection and storage. And a key principle they introduce is minimal sufficiency.
Right. Don't just collect everything. Collect what's sufficient. Quality over quantity.
Because you don't want a data swamp, you want the right data. And that influences the architecture. Era 1.0, storage was simple, local log files, maybe basic databases.
But Era 2.0 needs something more sophisticated for all this messy, multimodal data.
Definitely. You need a distributed, layered approach. Think fast caches like RAM for immediate working context, then local persistence layers like SQLite, RocksDB for stuff you need readily available, and finally cloud storage for long-term persistence and syncing across devices.
They use a code agent example, which makes this really clear. Building software over weeks. You can't rely solely on the model's context window. It's RAM.
No way. It's far too limited for that timescale. Systems like Claude Code tackle this by periodically saving the tasks, state what's been done, what's next, relevant code snippets into external storage. They call them structured notes.
So it's like creating persistent checkpoints.
Essentially, yeah. Lightweight, structured memory that lets the agent remember the project's state and pick up where it left off, extending its planning ability way beyond its immediate context window limit.
Okay, so we've collected the context, maybe stored it in layers.
Yeah.
Now, how do we manage the raw textual history itself? Say, a long chat log.
Yeah.
What are the options?
Well, raw dialogue is super high entropy. We need to impose structure. The simplest way is just timestamping. Easy to do, preserves order, scales well, but it gives zero semantic meaning. It doesn't tell the AI why something was said or how it relates to the overall goal.
Right, just a sequence of events, so we need to add meaning.
Which leads to tagging. Here, you assign functional roles, label this sentence as a goal, this is an action, this is a decision. It clarifies intent for the machine.
Okay, that sounds better. Downsides.
It can be really rigid. If the conversation doesn't fit neatly into your predefined tags, you either lose information or force it into a structure that doesn't quite fit.
Makes sense. What else?
The third approach is compression with hierarchical notes. Think of organizing the conversation like an outline, a tree structure. It looks clean, presents well.
But again, there's a catch.
Yeah. While it shows hierarchy, it often struggles to capture complex logical links across different branches. Cause and effect, subtle dependencies, those can get lost in a simple tree.
All right, this is where things get technically really juicy. Multimodal context. Handling text, images, audio, maybe sensor data all together. How do modern systems actually fuse this diverse stuff?
It's a major challenge, but crucial. The first step is usually mapping to a comparable vector space. You take each type of data text, pixels, audio waveforms, run it through its own specialized encoder.
So like a text encoder, an image encoder.
Exactly. Then you use a learned projection layer to map all those different feature representations into a single shared embedding space. The goal is that semantically similar things end up close together in this space, regardless of whether it was an image of a cat or the word cat.
Okay, so everything gets translated into a common vector language. Then what?
Then the real integration happens, often inside the transformer itself. One method is using a single transformer for self-attention. You feed all these projected tokens, image tokens, text tokens, audio tokens into the same transformer layers.
So they can all attend to each other.
Precisely. Layer by layer, an image token can learn to pay attention to a related text token and vice versa. This allows for that really fine-grained alignment we see in models like GPT-4 that understand images and text together.
Is that the only way?
Another common technique is cross-attention. Here, one modality, often text, acts as the query. Its features are used to selectively focus on relevant parts of another modality, like using a text query to find the specific object mentioned within a complex image. It's more targeted retrieval.
Okay, that covers getting context in. Now let's talk about context abstraction, or what they call self-baking. This sounds key, turning raw context into durable knowledge.
It is absolutely critical. This is what separates just having a temporary memory buffer from actually learning or building persistent understanding. Think of the OS analogy again. LLM is the CPU. Context window is RAM fast, but limited and volatile.
Right. As today, the short-term memory.
Self-baking is the process of taking important stuff from that RAM and writing it efficiently to the hard drive, the long-term persistent memory.
So how do we bake this knowledge? What are the strategies?
The simplest is just generating natural language summaries. Periodically have the AI summarize the interaction so far. It's flexible, easy to implement.
But probably not great for complex reasoning, just a block of text.
Exactly. It lacks structure, which leads to the second, more powerful strategy, extracting key facts using a fixed schema.
Like those structured notes for the code agent we talked about.
Very similar, but often more formalized. You define a specific structure like an entity map or fields for events, dependencies, rules, and the AI extracts information from the raw context to populate that schema.
The CodeRabbit example fits here, right? Creating a structured case file before reviewing code.
Perfect example. It builds an explicit representation of dependencies, project rules, team standards. That structure is what allows it to reason reliably about the entire code base, not just fumble through summaries. It provides a stable foundation.
Makes sense. Structure enables reasoning. What's the third self-baking strategy?
That's progressively compressing context into vectors. Here, you're encoding information into dense embeddings. You can do clever things like summarizing or merging older, less used embeddings into more compact forms over time.
Super efficient for semantic search, like an ARGA.
Incredibly efficient for retrieval, yes. The big drawback, though, is opacity. Those vectors aren't human readable. So debugging, inspecting the AI's memory, ensuring fairness or accuracy, that becomes much harder.
Okay, so we've collected, stored, and abstracted context. Now, how do we use it effectively? Specifically, selecting the right context. They mentioned that performance drops if the context window gets too full, like over 50%.
Yeah, that's a fascinating empirical finding. Even with huge context windows, just stuffing them full isn't optimal. You need intelligent filtering before the main processing. Attention before attention, as they put it.
So what guides that selection? How do we pick the best bits?
Several factors. Semantic relevance is the obvious one, finding chunks that are topically related, usually via vector search like RI, but also logical dependency, meaning context that's necessary for the current reasoning step. Systems like Mem1 actually try to trace a dependency graph to ensure they retrieve not just related info, but the specific prerequisites for the current task. And then simpler things matter too, like recency and frequency.
And when we do use RAG for retrieval, the filtering strategies for the source documents themselves are also important, right?
Absolutely. How you chop up the documents, segmentation matters. Fixed line or token windows are simple, but for code, you really need structure-aware segmentation, like using an abstract syntax tree, AST, that respects the logical blocks of the code.
Right, chopping a function in half is bad.
Very bad. And then the retrieval method itself. You can use semantic embeddings, non-semantic keyword search like grep, or even structured retrieval querying a knowledge graph.
Okay, let's shift gears slightly to multi-agent systems. These setups inherently use more context because you have multiple AI agents collaborating. How do they share and manage context effectively?
Good question. Coordination is key. The simplest way is just embedding context into prompts. Agent A does its work, generates a summary or a thought process, and that text block gets stuffed directly into Agent B's prompt. AutoGPT used this kind of chaining.
Seems a bit basic, maybe brittle.
It can be. A more robust approach uses shared memory. All agents read and write to a common centralized space. Often this is structured like a blackboard, maybe segmented by a topic or task.
Well, the TME system they mentioned, Task Memory Engine.
Exactly. TME models the whole process as a task graph. Each node is a reasoning step, edges show dependencies. The shared structured memory makes the context much more reliable and traceable than just passing messy text summaries back and forth.
Now, for the engineers listening, two really practical points they raise about building these systems day to day. First, KV caching. Crucial for speed and cost. What's the takeaway?
Cache hit rate is everything. And the key to a high hit rate is keeping your prefix prompts absolutely stable. Any tiny change, new timestamp, an extra space breaks the cache, forcing a full recomputation.
So you have to be super disciplined.
Totally. Enforce deterministic updates. Ideally, make context updates append only if possible. Treat that prefix like gold.
And the second point was about tool designing. The temptation is to give your agent tons of tools to make it powerful.
Big mistake, apparently. The research shows performance starts degrading significantly once you go past maybe 30 tools, and it falls off a cliff beyond 100 or so.
Why is that?
The agent gets overwhelmed by the choice. Descriptions start overlapping, making it hard to pick the right tool reliably. The advice is, keep the tool set lean and stable. If you need to constrain the agent, do it at the decoding level, not by constantly adding more tools.
Okay, let's ground this in reality.
Mm-hmm.
How do these principles show up in actual tools? They mention the Gemini command line interface.
Right. Gemini CLI uses special Gemini.md files to store persistent context. It cleverly uses the file system hierarchy, like folders, for context inheritance and isolation, similar to how config files often work.
And how does it handle long chat histories?
That's the key CE part. Instead of keeping the whole raw history, it periodically replaces older parts with AI-generated summaries following a specific predefined format. It compresses the history while trying to keep the essential meaning for future commands.
Smart. And what about really deep knowledge-heavy tasks, like the Tungi Deep Research example?
That system deals with super long interactions involving lots of web searches, reading papers, refining ideas. Its trick is using a specialized summarization model to create periodic context snapshots.
Like checkpoints again?
Kind of, but specifically designed snapshots of the research state. Subsequent searches and reasoning steps use these compact snapshots as their primary guide rather than trying to process the entire massive history. It's how they manage to conduct complex research over periods that would totally swamp a normal context window.
So looking ahead as we try to move towards that era 3.0, what are the big roadblocks? What challenges does context engineering 2.0 still need to solve?
The paper highlights a few major ones. First, and maybe biggest, is long context performance. Standard transformers have that $curry computational complexity. Double the context length, quadruple the compute time and cost. It's a killer.
Aren't there new architectures like Mamba that try to fix this?
There are, and they're promising. Mamba, long Mamba, low cost. They aim for linear scaling. But the paper notes they still seem to struggle sometimes with tasks requiring very long-range logical reasoning compared to standard transformers. It's an ongoing research area.
Okay, complexity is one bottleneck. What else?
System instability. When you're accumulating memory over long periods, weeks, months, small errors or misunderstandings early on can get baked in and cascade, potentially corrupting the entire memory state. Debugging that becomes a nightmare.
Right, garbage stays in and multiplies.
Pretty much. And related to that is evaluation. Our current benchmarks are mostly focused on simple retrieval. Did the RG system find the right document? They don't do a great job of testing the accuracy of abstracted memory or how well the system detects contradictions or if it can correct its own memory errors over time. We need better ways to measure long-term contextual understanding and reliability.
Which all seems to point towards that ultimate vision you laid out at the start, the semantic operating system.
Exactly. The solution isn't just making the context window infinitely large, it's building a smarter system around the LLM core, a system that actively manages memory. It needs to dynamically add, modify, and crucially, forget information intelligently.
And provide explainability.
Yes, self-explanation is key. You need to be able to trace why the agent made a decision, following the breadcrumbs back through its abstracted memory. It's about making context management a core, transparent, reliable function of the AI, not just a hidden implementation detail.
That's a really powerful vision. It feels like it ties back neatly to the paper's opening, where they invoke Karl Marx quite unexpectedly.
It was a surprising reference. Marx said the human essence is the ensemble of social relations.
And in our digital age, you could argue that ensemble is increasingly captured by our digital context.
Precisely. All our conversations, choices, creations, the digital breadcrumbs we leave, that's the context. And context engineering is about building systems that can collect, structure, abstract, and utilize that context.
So the final thought they leave us with. The human mind might not be uploadable, but our context, that can persist.
Absolutely. It can be managed, evolved, even interact through AI systems long after we're gone. In a way, context engineering is turning our digital trace itself into a potentially durable form of knowledge, memory, maybe even a kind of a digital identity. Something for you to definitely think about.